Hi everybody. I wanted to talk a little bit about polar intersections. So some of you might have noticed in that assessment last week, some funny things happened when you tried to find intersections of polar curves. So here are our two curves. We have r equals 2, which is the circle, and then r equals 4 sine 2 theta, which is the four-petaled rose curve here. Now to find the intersections of these two curves, which we need to do if we want to find the area of the region common to those two curves, uh, we did sort of what we would normally do. We put these two equations equal to each other, and then we solve. So we have 2/4 is the sine of 2 theta. The sine of 2 theta is a half. And then we just have to solve this equation. I like just to do this by thinking, all right, what angle has sine 1/2? Those angles are pi over 6 and 5 pi over 6. Those are the two angles from 0 to 2 pi that have that solution, right? So 2 theta is pi over 6 and 5 pi over 6, which means that theta could be pi over 12 or 5 pi over 12. Now this doesn't give us the full set of solutions from 0 to 2 pi. In order to do that, we need to extend this. So we could extend this by 2 pi. That would be 13 pi over 6. And then this would be 17 pi over 6, which would give us two more solutions, 13 pi over 12 and 17 pi over 12. Now, if we go back here, we see that we've got four solutions, four intersections at pi over 12, 5 pi over 12, a little bit less than pi over 2, 13 pi over 12, which is a little bit more than pi, and then 17 pi over 12, which is a little bit less than 3 pi over 2. So we only have four of the solutions. We know that there are eight. We can see that clearly. So where are the other four solutions? Now you might think that we could get those other four solutions by simply extending this. The next one here, we'd add another 12 pi over 6 to this. That would be 25 pi over 6. And sure enough, that gives us another apparent solution, but 25 pi over 12 is the same thing as pi over 12. They're coterminal angles. They differ by 2 pi. So that just gives us this solution again. So where are these other four intersections? So what's happening here is a consequence of the non-uniqueness of representation in the polar plane. Now this is something that we should know about. For example, here's the pole, and we think of this as the point 0, 0, but of course it could be 0 pi over 2 or 0 negative 17 pi over 51. In fact, it could be 0 comma any angle. The pole has infinitely many pairs of polar coordinates that identify it. It is not uniquely represented by a single pair of polar coordinates. In fact, no point in the polar plane is uniquely identified by a set of coordinates. I mean, this is the point 2 comma pi over 12, but of course it's also the point 2 comma 25 pi over 12, because you just go around a second time. In fact, it's also the point negative 2, 13 pi over 12, and so on. So this point has infinitely many uh, representations in polar coordinates. In fact, every point of the polar plane has infinitely many representations. And that makes finding intersections of two polar curves quite challenging, because this curve could pass through this point thinking it has one pair of coordinates, and this curve could pass through this point thinking that it has a different pair of coordinates, but it could be the same point. And that's exactly what's happening here, because these other intersections are happening when r is negative 2 for one of the functions. So if we instead solve the system r equals negative 2 and r equals 4 sine 2 theta, then that will give us negative 1/2 is sine 2 theta. So 2 theta is where sine is negative 1/2. That's 7 pi over 6 and 11 pi over 6. And that means that theta is 7 pi over 12, 11 pi over 12, and so on. So we could get 19 pi over 6 and 23 pi over 6, which will give us 19 pi over 12 and 23 pi over 12. So this point of intersection right here is the point of intersection let's see, that's going to be 19 pi over 12, which will be a little bit more than pi over 3 pi over 2, but backwards negative 2. So this is negative 2 comma 19 pi over 12. And so on the rose curve, this is thought of as having a distance to the pole of negative 2, whereas we're thinking on the circle having a distance to the pole of 2. And so this non-uniqueness of representation of points in polar can make it kind of tricky to find points of intersection between curves. This is something we take for granted when we work in the rectangular plane, because if you have a function like f of x is x squared minus x and another function g of x equals sine of x, you know that if these two functions intersect somewhere, they pass through the same point, they must have the same x coordinate and the same y coordinate. So that's why we can just set x squared minus x equal to sine x. They must have the same y coordinate. In polar, it's possible for two functions to pass through the same point, but that point have different coordinates for the two functions. And so you have to take that into consideration when you're trying to find intersections of functions in polar coordinates.